Hello, today I'm responding to some questions that were raised about my video in the A-level revision series on capacitors. The link to the specific point is shown here. I had said that the capacitor, which is consisting of parallel plates, the capacitance, or the value of the capacitance, is proportional to the distance. In fact, it's proportional to 1 over d, the separation between the plates. It's also proportional to the area of, as it were, overlap. So C is proportional to the area of overlap of the plate. And finally, I had said that C is proportional to the dielectric, which is a piece of insulating material that is sandwiched between the plates. And so C is proportional to epsilon. And from that we had drawn the overall conclusion that the capacitance equals epsilon, which is the dielectric, times area, the area of overlap, divided by d, the distance between the plates. And the questions I have been asked is, how does the dielectric play a role? How is the energy stored in the capacitor? Is the dielectric itself affected? And what happens if you remove the plate from the dielectric after charging and replace it with a new set of plates? Can you recover the charge? Well, we shall see that the last question doesn't really arise, but I'll try to explain as we go through. Firstly, let's just explain what this term epsilon actually is. Epsilon is usually expressed as K times epsilon naught, where K is the relative permittivity and epsilon naught is the permittivity of free space. We've met this before in the formula which tells you what the force is between two charged particles. The force is equal to Q1, Q2, where Q1, Q2 are the charges on the two particles, divided by 4 pi epsilon naught r squared, where r is the separation of the two charges and epsilon naught is this epsilon naught, the permittivity of free space. And epsilon, in other words the dielectric constant of the insulator between the capacitors, is equal simply to a constant for that dielectric times the permittivity of free space. Sorry about my dog barking. The value of epsilon naught is 8.85 times 10 to the minus 12 farads per metre. And you'll see you need that term to be farads per metre because the capacitance is in farads, area is in metre squared, distance is in metre, so area divided by distance is metre. So farads per metre is what epsilon has to be. So let's remind ourselves what happens when a capacitor is charged. Here is a battery and we connect it to a parallel plate capacitor. And what happens is that the electrons flow onto this plate. Sorry, that's not minus, it is minus, not plus. The electrons are on that plate. They will repel the electrons from this plate and leave behind positive charges. And so the capacitor is charged because the electrons flow onto this plate, they repel the electrons from that plate and leave positive charges. No current flows across the gap. Very important to stress that. Now let's say that the charge on this plate per unit area is sigma minus, and the charge per unit area on this plate is sigma plus, and they will of course be equal and opposite. Now we remove the battery, and in those circumstances the charged capacitor remains charged. The charge can't go anywhere. We've taken the battery away. There's nowhere for the charge to flow. It must just sit there. And because there's a positive charge on this plate and a negative charge on this plate, there will be an electric field in that direction between the two plates. Now let's insert the dielectric. So here's the capacitor again. This plate is positively charged. this plate is negatively charged. And now I'm going to insert the dielectric, and that will be an insulator. And the point about an insulator is that there are not a large amount of free electrons to flow. That doesn't mean to say that there aren't any, it just means that there aren't very many. So what actually happens to the dielectric? Well, the electrons that are free in the dielectric will be repelled from this positive charge. And so there will be an induced negative charge right at the surface of the dielectric. Remember, the dielectric is an insulator, so there will not be a flow of charge inside. But right at the edges, the electrons will be repelled by this positive charge. And likewise, the positive charges will be repelled, the electrons will be attracted by this positive charge. And likewise, at this edge, the electrons will be repelled, leaving an induced positive charge. So here you've got the surface charge on the plate, which we're going to call the free charge. And here you've got the negative free charge on this plate. But here you've got a negative induced charge on the dielectric, on the surface of the dielectric. And here is a positive induced charge on the surface of the dielectric at this end. That means that you've got an electric field, which we might call the free electric field, between the positive and the negative plates. But you've also now got an induced field between the positive and negative edges of the dielectric, and let's call that E induced. So the net field in this direction, in the downwards direction, is going to equal the free field between the two plates minus the induced field between the two edges of the dielectric. Now let's make an assumption which turns out to be a reasonable assumption, that the charge per unit area in the induced part of the dielectric is equal to a constant times the free charge. In other words, the amount of charge that is induced on this surface is a direct proportionality to the amount of charge on the plate itself. Well, if that's the case, you can also say that the E induced equals B E free. In other words, the induced field between the edges of the dielectric is a direct proportion of the free field that is flowing between the plates, since the strength of the field is proportional to the amount of charge. You'll be able to see that in my video on fields in the A-level revision series. And that means that since E induced equals EF minus E induced, and E induced is B times E free, that means that E net is equal to E free into 1 minus B. And 1 minus B is K, the dielectric constant, or the relative permittivity. That's the K that we established all the way back up here. So that means that epsilon equals K times epsilon naught. The permittivity of the dielectric, or the dielectric constant, is equal to the relative permittivity times the permittivity of free space. For glass, K is 5. For water, K is 80. So since the capacitance equals epsilon, which is K epsilon 0, times the area of overlap divided by D, what that means is that if you put a glass dielectric between the two plates, then the capacitance will be 5 times greater than if you had not had the glass between the plates. Now the impact of all that depends on precisely what you do. Here's the first experiment that we're going to do. We take our battery, we're going to now put an ammeter in the circuit, and here is the capacitor, and when we switch on the battery, then we're going to see the capacitor charge up, negative this end, positive at that end, and there will be a certain capacitance which will equal epsilon A over D. And epsilon, for the moment, is 1, because this is just free space. We haven't put the dielectric in yet. Now we insert the glass dielectric it's sandwiched between the two plates. And of course there will be the induced charges at the edges. But what we say is that the dielectric constant is now 5 times higher, because epsilon equals K times epsilon free space. So if K is 5, then C will be 5 times higher. So simply by putting the dielectric in, the capacitance will increase by 5 times, and C is Q over V. Now V is the voltage on the battery, and that's not changing because the battery is still connected. But C has increased 5-fold. So immediately you can see that Q will increase 5-fold. In other words, a lot more charge will flow onto these plates, and you will see a current flow in the ammeter, because more charge, as soon as you put that dielectric in, more charge will flow. That means a current will flow, and there will be more charge on the plates. What does that mean in terms of energy stored? Well, in my previous video on capacitors, I said that the energy is half QV. I'll demonstrate why that's the case in a moment. But since the charge has increased 5-fold, but the voltage remains the same, that means that the energy will increase 5-fold. So before you put the dielectric in, the capacitor would have a certain stored energy, which would be half QV. When you put the dielectric in, the charge increases 5-fold, and so the stored energy, potential energy, increases 5-fold. Now let's take a second case. This time we're going to charge up the capacitor in the usual way by putting a battery across the two plates, and we shall end up with the two plates charged positive and negative. But now we disconnect the battery. So the capacitor is just standing there isolated. The charge cannot go anywhere. It is fixed and it is trapped. Now we introduce the dielectric. We're going to use a glass dielectric again, and once again we shall get induced charges right at the edges of the dielectric. Once again, C equals epsilon A over D. And effectively the dielectric has increased 5-fold, so the capacitance has increased 5-fold. And C is Q, charge over voltage. But now the charge cannot, unlike up here, the charge cannot increase 5-fold, because here it could, because there's more charge to come from the battery. But here there is no source of any extra charge. That charge is now fixed and trapped. You can't get any more charge. So if the capacitance increases by 5-fold, the only way that can happen is if the voltage decreases 5-fold, because the charge can't change. So that means that the voltage across the plates goes down by 5. And since the electric field is equal to the voltage times the distance, the electric field is effectively volts per meter, that means that this field across the plates has fallen to a value of 1/5 of what it was before. What about the energy? I'm guilty of using E for both electric field and energy. Up here I should have said that this is energy. is half QV. And here, energy is a half times Q times V. Now in this example, what does that mean? Well, Q is unchanged. There's no source of any extra charge and it can't go anywhere, so Q is a constant. V, we've just said, decreases by 5. So the energy goes down by 5-fold. But here's the question, and I think this is probably what the questioner was getting at. Where has that energy gone? And the answer is that that lost energy, as it were, has gone into an electrostatic force between the capacitor and the dielectric. Think of it, you see, as you start to put that dielectric in, there becomes an induced charge on the surfaces, and now you've got a situation where the positive charge on the plate is going to attract the negative charge that is on the surface of the dielectric. And down here, the negative charge on the plate is going to attract the positive charge on the dielectric. So actually, that capacitor will pull the dielectric in. And it is using energy to do that, and that's where this lost energy is gone. And if you want to get that dielectric out from between the capacitor, whilst it is still charged, you will actually have to physically do work to get it out. You will have to give it energy to get it out from between the two plates. And then you will restore the capacitor to its original energy, because it will go back to having its original voltage and thus its original E field. Now it might just be worth explaining what that energy is that's in the capacitor, and we'll think of it not in terms of how you put energy in, but how you might get energy out. For electricity, the power is equal to the voltage times the current. If you have an ordinary circuit, battery, resistance, and a current flowing, then you can say, and the battery is V, you can say that of course V equals IR, that's simply Ohm's law, but that power is V times I, the voltage times the current. Energy therefore, which is power times time, is VI, which is the power, times T in seconds, because power is energy divided by time. Now, IT is simply charge, because current is charge flowing in a particular time. And Q is equal to VC. That's how we measure capacitance. Capacitance, you remember, is charge per volt. So that means that we can take this formula here, energy, and we can say that energy is VIT. Well, V we can say is Q over C, and IT is Q, and that's Q squared over C. But there's a mistake here, because of course what we're talking about is discharging a capacitor. So here's a fully charged capacitor, and we discharge it through, say, a resistance, which might be a kind of a flash bulb or something like that. And the charge will flow, and it may take T seconds, and the current will flow. But of course, it won't be the same current throughout, because as the charge flows, there will be less of it, and the charge will actually reduce from the maximum charge to 0. So in fact, the average charge that flows throughout that whole process is half the total charge on the capacitor. So in fact, the energy is not Q squared over C, but a half Q squared over C. Because as I've said, the charge doesn't remain the same as it flows through here. The charge is actually going down to 0. So on average, you've only got half the charge flowing around the wire. And of course, because Q equals VC, you can also say that energy equals a half Q times V. And since that is the energy that is dissipated through the resistance as you discharge the capacitor, then it must also be the potential energy that sits on the capacitor, or is stored within the capacitor, before you discharge it. So when you charge up a capacitor, its total potential energy is half QV. And if you then discharge it, that energy will be discharged through whatever you discharge it through. So I hope that deals with the questions that I've been asked. Let's just review the questions and a summary of the answers. Question 1 was, how does the dielectric play a role? Well, the answer is the surface of the dielectric has an induced charge. That induced charge creates a field in the opposite direction and thus reduces the overall field, and what we find is that the capacitance therefore varies. How is the energy stored in the capacitor? Well, I try to explain that here. It is stored as potential energy such that it can be released if you connect the capacitor to some sort of circuit. That energy will flow as a current through a resistor and discharge in that way. Is the dielectric affected? Yes, it is. The dielectric has an induced charge on it, and it's that induced charge that creates a field within the dielectric that opposes the field between the plates, and that's what changes the capacitance. For the final question, what happens if you remove the plates from the dielectric after charging? Well, I suppose removing the plates from the dielectric is the same as removing the dielectric from the plates. And the answer is if you take the dielectric out, then you are just left with a fully charged capacitor. Once again, remember the charge can't go anywhere, and so the capacitance goes back to what it was before you put the dielectric in the first place. I hope that helps. Permittivity, and epsilon naught is the permittivity of free space. We've met this before in the formula which tells you what the force is between two charged particles. The force is equal to Q1, Q2, where Q1, Q2 are the charges on the two particles, divided by 4 pi epsilon naught r squared, where r is the separation of the two. From that we had drawn the overall conclusion that the capacitance equals epsilon, which is the dielectric, times area, the area of overlap, divided by d, the distance between the plates. And the questions I have been asked is, how does the dielectric play a role? How is the energy stored in the capacitor? Is the dielectric itself affected? And what happens? Hello, today I'm responding to some questions that were raised about my video in the A-level revision series on capacitors. The link to the specific point is shown here. I had said that the capacitor, which is consisting of parallel plates, the capacitance, or the value of the capacitance, is proportional to the distance. In fact, it's proportional to 1 over d, the separation between the plates. If you remove the plate from the dielectric after charging and replace it with a new set of plates, can you recover the charge? Well, we shall see that the last question doesn't really arise, but I'll try to explain as we go through. Firstly, let's just explain what this term epsilon actually is. Epsilon is usually expressed as K times epsilon naught, where K is the relative It's also proportional to the area of, as it were, overlap. So C is proportional to the area of overlap of the plate. And finally, I had said that C is proportional to the dielectric, which is a piece of insulating material that is sandwiched between the plates. And so C is proportional to epsilon.